Pop quiz. If you were able to look back on the present from deep in the future, what age would you say we're living in?
Is this a trick question? I mean, I want to say information age, but it seems too obvious. Can I say more than one age?
Yeah, I think it is safe to say that we are living in more than one age. From the beginning of humanity, we've seen prevailing technologies marked with milestones. The Stone Age, the Bronze Age, the Iron Age, all occurring many thousands of years ago. Man's mastery of these materials has defined us. But by that metric, the last couple of hundred years have seen a flurry of ages. The steam age, the industrial age, the atomic age, the television age, the space age, to name but a few. But those are not the answers I was looking for.
Is that a clue?
Yes, it is. I think that this age could be classified as the Glass Age.
That's not what I was thinking.
I know.
So how are we in the Glass Age?
Well, let me put it to you this way. Can you imagine a world without glass? Now, I don't want a cheeky answer. I want you to really think about it.
Okay, no. I can't imagine the world without glass.
Exactly. Glass is really quite extraordinary. Without it, many of our major accomplishments would never have happened. Glass has a deep and complex history, and as a material, it has properties and characteristics that we are only just beginning to understand. We look right through it and think of it one-dimensionally. Most of us think of glass as a fragile, brittle thing that, if not handled correctly, will break in a spectacular fashion.
So you're going to break that to make a point?
Indeed.
Can I help?
Yes, you can. And it's true, our everyday common variety of glass is brittle, but it doesn't have to be that way. Glass has already altered our lives and is behaving in ways that is totally unexpected.
Got it.
Let's start with a history of glass.
I think I can handle that. Glass as we know it is most commonly made of silica, the primary ingredient of beach sand. Mix silica with a couple of other key ingredients, heat it all up till it melts, and bang, you got glass. Humans have been making glass since ancient times, starting with beads, vessels, and ceremonial accoutrements. Glass-making techniques spread out from Mesopotamia, culture to culture, changing in incremental ways for much of the last 4,500 years or so. The Romans even had glass windows on their important buildings as early as the 1st century AD. Glassblowing was discovered around that time, and soon inexpensive and ubiquitous glass became one of the hallmarks of the Roman Empire. But no period has seen such growth in the development of glass technologies as in the last 150 years. We've been able to unlock the secrets of glass in ways that would have seemed like magic to our forebears.
Nice.
Thanks.
So tell me what's so special about the last 150 years?
Well, several things. In that period, technology evolved at an exponential rate. With that came tools and processes that enabled advancement across all material sciences. The leader in glass material science was, and still is, an upstate New York glass company that started out in the mid-1800s, Corning Incorporated. One of their first products was a toughened glass lens for railroad signal lanterns that offered two radical improvements over any other lens of that time. It could be produced in a consistent color, and more importantly, it didn't break when rain hit the hot glass. This helped save lives by bringing down the number of train wrecks, but it also set a course for 160 years of innovation in glass. Of course, everybody knows about Corningware and Pyrex products too. Those innovations came from Corning during the early part of the last century.
You know, I have tons of this in my kitchen.
But Corning no longer makes kitchenware. They've innovated way beyond that. Let's take a look. We'll start with this.
Ah, optical fiber.
Right, optical fiber. This does two things, both astonishing. The first one is this.
That right there is pure glass. A glass strand inside the cable, tightly wound around a pencil and yet not breaking. When you stop and think about it, that is a mind bender. Okay, what's the second thing?
Well, it's the way the light moves through the glass. When the glass is bent this way, you'd expect light to leak out and get weaker and corrupt the data that it carries. But that's not happening. Nearly all the light entering this optical fiber is coming out the other end.
So it has a low attenuation?
Yeah, exactly. Very low. In the late 1960s, Corning figured out how to limit the attenuation or loss of light as it travels through fiber, even when that fiber is bent.
Nice.
This discovery led to the practical use of fiber as a medium for voice and data communications over great distances, ushering in an era of low-cost, high-bandwidth communications and ultimately the internet as we know it.
Wow. So just how much data can these optical fibers carry?
This video playing back right here is sucking in data at around 20 gigabits per second.
That is a lot of data.
Yeah, this is ultra-high definition raw video, but even in this case, the optical fiber is not anywhere near capacity. The bottlenecks are here and here, not here. The practical limit of data transport over optical fiber keeps increasing. Using today's technology, it's possible to transport more than 1 million gigabits per second, about a petabit. That'd be like downloading 17,000 high-definition movies from Netflix in a single second.
That's amazing. Okay, tell me about this stuff.
Well, obviously it's an optical fiber as well, but instead of sending light through one end and out the other, it emits light throughout its entire length.
Cool. What's it good for?
I have no idea. Okay, so I was able to seriously bend a strand of glass. Didn't break. But what do you think's going to happen when I try to bend a pane of glass? Rhetorical question. Check this out.
That doesn't look like it went very well.
Well, that was soda lime glass, the kind of normal stuff we see around us every day. But watch what happens next. This is glass too. It's called Willow Glass, also made by Corning. And it's flexible.
No way! I cannot believe that is glass.
Well, it is. There's no trickery here. This is glass, but it's as flexible as paper.
So what kind of applications does that have?
Well, that's where it gets really cool. Check this out.
All right, it looks like a piece of stainless steel. And what is this? Willow glass bonded to one side as a scratch-resistant coating?
Yep.
Okay, but tell me this, how is the willow glass anywhere near as durable as stainless?
Well, that's a good question. Watch this.
That is amazing! I cannot believe that the blade did not shatter the glass.
It didn't. And that's just half the story.
All right, so what are we doing?
Give me that.
Okay.
Take this.
This is heavy, man. What do you want me to do with it?
I want you to drop that right on that piece of stainless steel with the willow glass on it.
Seriously.
Let's see what happens.
Here we go. 3, 2, 1. No way!
It dented it, but it didn't break the glass.
That is insane.
And you can attach this to just about any solid surface.
Bendy, flexible, durable glass. Impressive. And characteristics you wouldn't normally associate with glass, right?
Right. I like this new glass age we're in.
Let's switch gears. Your smartphone. You hold it in your hand, you put it to your ear, you keep it in your pocket or your purse. It's a great everyday use of glass that you might not think about.
Till it breaks.
Until it breaks. I myself have shattered over a dozen of these, but you might have noticed over the years that the display on your phone has been getting harder to break. Let's go back a few years. If you'd done that to your standard 2008 phone, that's what would have happened.
Not pretty.
No, and that could easily happen just by keeping your keys and your phone in the same pocket. And if you then dropped that phone, well, the probability of the phone breaking was high.
How high?
Very high. Let me show you.
Aren't you going to drop the phone?
Well, sort of. Instead of dropping the phone, I'm going to drop something on the phone, this steel ball.
For consistency's sake.
Exactly. In this way, my phone drops exactly the same way every single time. Here we go. 3, 2, 1. Oh.
I've seen you do that so many times in real life.
Me too. But that was then. This is now, thanks to Corning, we have Gorilla Glass.
I'm pretty sure that's what I've got on my phone.
And it's on this phone as well. I'm about to do the same test a second time. Check this out.
No scratch.
Not at all. Now, same drop test. Ready?
Yeah.
3, 2, 1.
Wow. What a difference a few years can make.
Actually, Corning came up with this method for strengthening glass long ago. Gorilla Glass evolved from that process and today is found on all the best small devices like this. It's beginning to find its way onto larger format displays too. Now, it's not unbreakable. If you set out to break it, you will. But as Corning figures out ways to unlock more secrets of glass, it will continue to get more resilient. It may even get to a state where devices such as these simply don't break anymore. Oh, and by the way, Corning has just come out with a new and improved version of Gorilla Glass.
Really?
Yeah. Let's go deeper. Watch this.
Hot stuff.
Yeah, this hot stuff is your basic everyday soda lime glass. There's nothing remarkable about it except that it's white hot and molten. There we go, and I'm going to drop it in cold water. It's called a Prince Rupert drop.
Who's Prince Rupert?
Some Bavarian from the 1600s. He came up with this. Okay, so there's a few things going on here. The cold water rapidly cools the exterior surface of the glass, hardening it almost immediately. The interior, still molten, cools more slowly. As it cools, it contracts and attempts to pull the surface in with it, but it can't. Well, not very much. The surface is already hardened, so it gets pulled in only a little, compressing it while also creating an internal layer that remains forever under tension. It is this action that gives the glass its uncharacteristic strength. We call it compressive strength.
It sounds like the same principle as how an arch provides strength in structural engineering.
Yes, kind of. Now, Jamie, I'm going to ask for your help. We're going to attempt to destroy this Prince Rupert drop. I just want you to tip that hammer past its center point. Go ahead.
I feel like we've been swindled.
Swindled not. We have just experienced the power of compressive strength. It does, however, have an Achilles heel. Take those nippers right there and nip the backside of the tail of this Prince Rupert drop and watch what happens. Wait. Cue the high-speed camera. Okay, here we go. Whoa! That was even cooler than I thought it would be. That is what happens when you release the stress in compressive strength glass. The whole thing shatters.
Spectacularly.
Yes, well, at least in that example it was. That's because the stress was so great between the outer compressive layer and the inner tension layer.
That when released, it was a catastrophic result.
This is Gorilla Glass. It has been refined over time, but like all Gorilla Glass variants that came before it, it is compressive strength glass. But it's not made in the same way as we just demonstrated, the rapid cooling method. No, instead, Corning uses an ion exchange process. To break it down simply, the surface ion particles that naturally form during the manufacture are replaced with larger ion particles. Once exchanged, the larger ion particles create the same sort of inward pressure that we see on the Prince Rupert drop. And with this method, they are able to control and manage the resulting tension.
I think what you're saying with this process is that they're able to tune strength in the glass by dialing in the right balance between compression and tension?
Yeah, that's a great way of saying it. That, and also by adding in a few other tricks that change the molecular structure of the glass. Corning is steadily moving forward towards the Holy Grail.
Thin, unbreakable glass for our mobile devices?
Well, maybe not unbreakable, but yes, thin and very tough. And by the way, the applications for this tough glass go well beyond mobile devices. Let's go over this way. Behold, the common automobile windshield made from regular soda lime glass. It's quite strong because it's very thick and it's laminated, which means it's two pieces of glass bonded together using resin in the middle. And the resin does two things. It gives it added strength and it holds the glass together on impact. You've probably seen broken windshields before. Lots of crazy cracked glass, but still mostly held together in the shape of a windshield.
Like this. That's pretty cool.
Yes, it is. Windshields have been made of laminated glass for the last 100 years, and they've served us well. But there is a big drawback.
I think I know what you're going to say. It's heavy.
Yes, very heavy. And as we strive for more energy-efficient cars and trucks, the weight of all that glass can be a bit of a problem.
I have a feeling you're about to show an alternative.
Yes. Take a look at this. Now, this is also a laminate windshield, but it's not one you'd find in production. It's experimental, which is great because we're going to experiment with it. It has regular soda lime glass on its outside surface and resin in the center like the other one, but this windshield has Gorilla Glass on the inside surface.
Sweet. It looks thinner.
Yes, it is. And a lot lighter, too. In fact, just by changing the one laminate, the overall weight is reduced by about a third. In a car, that adds up fast.
Thinner, lighter, and let me guess, it's just as strong as windshield A.
Well, maybe. Let's find out.
Oh, goody.
Okay, wait, no, you don't need the sledgehammer for this one. Put that down. Instead, you're going to shoot this windshield with an air cannon.
Cool.
No, don't get too excited. We're going to have to mount this, tie it down so it doesn't wobble, and we're going to simulate a pebble hitting this windshield at a super high speed.
Good enough for me. When do I start shooting?
Well, before we shoot the Gorilla Glass laminate, let's shoot the regular soda lime laminate, windshield A. This way. All right, here we go. Perfect. You want to do the honors?
Sure.
I'll count it in. 3, 2, 1, go!
Whoa.
That was a lot of damage.
Can we see that in slow motion?
The ball bearing hits the windshield at around 120 miles per hour. This could be a stone flicked up by another car. It penetrates the exterior glass, it stretches the resin, it's slowed down a bit, but it still has momentum to break the interior glass layer, causing small fragments of glass to spray out through the interior of the car.
Not good.
So let's try windshield B. The Gorilla Glass didn't appear to break. The foil is intact.
Let's see it in slow-mo.
The ball bearing hits the windshield at around 120 miles per hour just as before. It goes through the front layer of soda lime glass, stretches the resin, but doesn't have enough energy to break the Gorilla Glass. It's not bulletproof. I'm pretty sure if we turned up the velocity, we'd breach the Gorilla layer too. But in this test, and all things being equal, it performed a lot better than the thicker, heavier soda lime laminate windshield. That's impressive. What we're seeing here is compressive strength at its finest moment.
Okay, so it's lighter, thinner, and stronger. That's pretty good.
Yes, it is.
Can I get this on my car?
Not today, but soon, I hope. Come on, though. After living through the Iron Age and the Bronze Age, you could wait a little longer. Actually, when you think about it, the application for this goes way beyond the car, doesn't it? Ah, yes. Feels good to be in the glass age. Come on.
Don't touch me.
Sorry.